we will move on to a 12 pulse LCC. So, why we directly jumped from 6 to 12? The answer lies in how we got 6 first of all. How we got 6? You recall, we derived that. Okay. Now, we first said that it should be a multiple of 3, it will help. Then we saw that a multiple of 6 will help. So, the first possible circuit is 6 pulse. The next one is 12 pulse. As the name suggests, there are 6 pulses in the 6 pulse converter, 6 pulse gate pulses given. In the case of 12 pulse, there are 12 pulses given. Now, there is one gate pulse which is given. Now, there is also pulsation on the DC side. Okay. So, the number of pulsations is giving the pulse number. At the same time, since we are using the switching frequency as nothing but the AC side frequency, it is also the number of gate pulses you give, that also gives the pulse number. So, in the case of 6 pulse, in each cycle we give 6 pulses because there are 6 thyristor valves. In the case of 12 pulse, there are 12 thyristor valves. So, we give 12 gate pulses to these thyristor valves. So, what is the circuit? So, we will first draw the circuit, then try to see what advantages do we get with 12 pulse. So, why should we go first of all from 6 pulse to 12 pulse? I mean, higher pulse number, what is the use? Okay, we will see all those, we will answer all these questions in detail. Let me first draw the circuit. So, there are 2 transformers which are used in a 12 pulse LCC. One transformer is YY connected and another transformer is Y delta connected. So, there are 2 transformers. There is one YY connected or star star connected, one is YY connected and the other one is Y delta connected or star delta connected. Okay. So, let me draw the circuit diagram. Now, this is the circuit diagram of YY connected transformer. So, we normally use what is known as a dot convention. So, each winding is a 3-phase winding. If you take any phase, A phase or B phase or C phase, the dot actually means that terminal which is always having the same polarity with respect to the other terminal for the both windings. See, suppose I take this as A and this as A phase. So, the dotted terminal of both these windings are at the same polarity with respect to the other terminal which is does not have a dot. That is the purpose of dot convention. Okay. So, let me say the number of turns here is N1 and the number of turns here is N2. So, this is the YY transformer. There is one more transformer, Y delta connected transformer. So, one side is Y, the other side is delta. Now, we show the windings belonging to the same phase in parallel. See, for example, in the YY case also, if this is A phase and this is A phase, they are shown parallel. Okay. So, similarly, if I take this as B phase and this as B phase, they are shown in parallel. This is C phase and this is C phase, they are shown in parallel. Okay, even while drawing we show it in parallel, I mean it will help us. So, here also the windings belonging to the same phase will be shown in parallel. See, that means the flux linking each turn of the A phase winding on the primary is same as the flux which is linking the one turn of the other A phase winding. Okay, that is what it means. So, suppose I put a dot here, dot here, dot here, and you would have noticed not only showing in parallel, if the dot, if you look at the A phase, the dot is above in the primary side, here also on the secondary side also it is above in the YY case. Okay. The same thing is applicable even here. So, if this is A phase, this is A phase. Oh, sorry, I made a mistake. So, this is A phase. Similarly, if this is B phase, this is B phase, and if this is C phase, this is C phase. So, if you look at B phase again, if the dot is shown to the right on the primary side, even in the secondary side we show it to the right. Okay. So, I mean this, I wrote this ABC just for the sake of explanation. I mean I no longer need this in the further analysis. I will erase this. It was just written for the sake of showing the dots and the location of the dots. Okay. So, the number of turns here is also N1. So, we will see what should be the number of turns in each winding on the delta side. So, before that, to answer that question about the number of turns, we will complete the circuit. So, the idea is to have two 6 pulse LCCs. So, we have two 6 pulse line commutated converters. So, this is one 6 pulse line commutated converter. So, there are 3 terminals that are brought out on the AC side. So, I connect this terminal of this winding of the YY connected transformer to this AC side terminal of the 6 pulse LCC. This is connected to then there is one more 6 pulse LCC and we connect the terminals of this delta side to the AC side terminals. And there are two DC sides corresponding to the two 6 pulse LCCs, what we do is we connect the negative terminal of the first 6 pulse LCC to the positive terminal of the second 6 pulse LCC. So, finally, we get only two terminals here on the DC side of the 12 pulse LCC, and we also short the terminals of the Y side of the two transformers. So, I take this terminal of the Y side of the first transformer and connect it to this terminal of the second transformer Y side. Okay. Then I take this terminal and connect it to this terminal, and finally take this and connect it to this terminal. And I also bring out these three terminals corresponding to the three phases. So, this is one terminal. This is one terminal. This is another terminal. And I will give some names for the currents that flow into the AC side of the 6 pulse LCCs. Now, I use the complex notation or phasor notation, so not the instantaneous, the phasor notation. So, the AC side currents are not just sinusoidal, they have harmonics. So, what are the harmonics that are present on the AC side in the currents? Huh? So, what is the first harmonic that is present? What is the order of the first harmonic? 5th, then 7th, then 11th, 13th, so on. Okay. Now, there is a fundamental component as well as harmonic component. So, I use a notation like this. This is A phase current. So, I with a subscript A and another subscript H, and since this is complex, I put an arrow IAH. Now, here this H on the AC side, what we mean is H takes a value of either 1. So, if it takes 1, it is for fundamental component. And if it takes a value 6k plus minus 1, where k is either 1, 2, 3 or so on up to infinity. So, this is for harmonic components. So, what I am trying to say here is at a time I take one value of H. So, the possible values of H are on the, see this is please note this is the AC side. So, the possible values of H are 1 for fundamental, 5, 7, 11, 13, 17, 19 so on. So, at a time I take one value of H. So, like that I can do analysis for all the values of H. Similarly, if I take the next B phase, the current here is, okay, let me take the current here is IBH, and the current that is flowing in this wire is ICH. Now, there are currents flowing into the AC, I mean in the AC side terminals of the second LCC also, 6 pulse LCC. So, I call this current as IAH prime. Then the current here is IBH prime. And the current that is flowing here is ICH prime. Okay. Okay. Now, there are a few more things that are left out here. I did not say what is the number of turns in the delta side winding. What should be the number of turns? Root 3 into why? Yeah, the line to line voltage which is applied to the AC side terminals of the 6 pulse for both should be same. Okay. So, if I supply the primary winding with the same voltage, they are connected in parallel. Please note that primary windings are connected in parallel. So, if I apply a voltage on the primary side and if I want the same magnitude voltages to be applied to the two 6 pulse LCCs, the number of turns should be root 3 N2. So, whether it is this winding or this winding or this winding, the number of turns is root 3 N2. Okay. Now, I will also show some currents which are flowing through this delta connected windings. Now, what will be this current? What subscript can I use, A, B or C? B. Please note, look at IBH, the current which is flowing through this. Okay. So, this winding is parallel to this. So, this is also B phase winding. So, whenever there is a B phase winding, I will use the subscript IBH. To differentiate between the other two currents, I use a double prime. Okay. So, notice that I have shown the currents as entering the current as leaving the dots in the first YY, the secondary side of the YY transformer, also in the delta side of the second transformer. Then if I want the current here, this is A side or A phase or B phase or C phase. This is nothing but A phase, IAH double prime. So, here also current is leaving the dot, and finally, the current here is C phase current, ICH double prime. Okay. Now, I will also show the currents that flow in these wires. Okay, let me take one by one. What is this one? The current here, A phase current or B phase or C phase? A phase. So, it is IAH. I use an uppercase A just to differentiate from the other. So, here the current is entering the dot. It is a primary winding, current is entering the dot. Then the current that is flowing here is phase, which B? The B or C? B, IBH, and this is C phase. So, I use uppercase ABC for the currents here. Now, on the DC side also there are voltages, the DC side voltages, but the harmonics in the DC side voltage are not of the same order as the currents harmonics on the AC side. See, this is on the AC side, the definition of H. Now, if you look at the DC side voltage, what is the order of harmonics? It is multiple of 6. Okay. So, on the DC side, we say H equal to 6K, K equal to 1, 2, 3 for harmonic components. Now, if you say harmonic component is a sinusoidal waveform. Only thing is it has a frequency depending on the order of the harmonic component. So, you would have noticed that, see, when I say IAH, where H is 5, it is a fifth order harmonic component, so it is sinusoidal. So, if I have sinusoidal quantity, I can represent it by a phasor. So, I use an arrow over the notation to mean that it is a complex quantity. So, it has a magnitude and an angle. Similarly, if I take the voltage on the DC side of this 6 pulse LCC, if I take any harmonic quantity, it is a sinusoidal quantity. So, I can still represent that by a phasor, say VH. Say the average is DC, but the harmonic is AC. The harmonic is sinusoidal, so I can represent it by a phasor. So, similarly, I take this 6 pulse LCC, I call the harmonic component as VH prime. Okay. So, the definition of H is different for DC side and AC side, please note that. Is this clear? The definition of H is different for AC side and DC side, that is what is written here. Now, if I want to analyze this, so what I suggest is that this is the circuit of the 12 pulse LCC. So, it consists of 2 6 pulse LCCs and 2 transformers, one YY connected, one Y delta connected. So, the question is, why should one go for 12 pulse? So, I mean what is there in 6 pulse which is a disadvantage which will go away here? I mean obviously there should be some advantage of this with respect to 6 pulse, that is why we make some complicated arrangements and go for 12 pulse, right. So, we will see what is the purpose of going for 12 pulse, but for that we need to do some analysis, and for simplifying the analysis we will make one assumption that the transformers are ideal. So, the assumption is transformers are ideal. So, it actually means that there is no resistance, no leakage, no core loss resistance, no magnetizing inductance, all these are not there in the ideal transformer. Now, if we decide that the number of turns in the delta connected winding should be root 3 N2, I mean we know what is the purpose of that. We said that the voltages should be same, the magnitude of the voltage should be same. Now, if I give gate pulses at some instant to the first LCC, okay, suppose I say this is valve 1 of the first LCC, this is valve say 1 prime. Now, if I give the gate pulse to valve 1 at some instant, do I give the gate pulse to valve 1 prime at the same instant? If not, when should I give? 30 degrees. Now, the reason is because of Y delta transformer, the voltages that are applied to the second LCC are lagging or leading the voltages applied to the first LCC. With respect to the voltages applied to the first LCC, the voltages that are applied to the second LCC are lagging or leading. So, to explain which one is lagging, I will show the 2 transformers. Now, I will show you on the dot. So, we know all these things, all these windings have N1 turns, and this is N2, and these 3 have root 3 N2, all the 3. Okay. So, let me call this voltage as VA, and let me call this voltage as say VB. What I mean, let me use the same. So, I took this is A phase and this is B phase, sorry. So, this is A phase VA, this is VB. So, this is phasor VA, phasor VB. Okay. Similarly, this is VC. So, this is terminal A phase, B phase and C phase. So, let me call this as A, B, C. Now, between A and B, what is the voltage? Suppose I take okay, let me suppose I take one of these as reference. Okay. So, let me assume that I have only sinusoidal voltages. So, suppose V B is some V at an angle 0, then V C is the same voltage magnitude at an angle minus 120. So, if I want the voltage between B and C, it is V B by Kirchhoff's voltage law, it is V B. In terms of V B and V C, I can say what is the voltage between B and C by Kirchhoff's voltage law, it is V B minus V C. Okay. So, it is V B minus V C. So, what is V B minus V C? V at an angle 0 minus V at an angle minus 120 will give me what? What resultant magnitude is root 3 V at an angle 30 degrees. Now, if I take between B and C in the delta, say I took between B and C. So, here between B and C it is V B minus V C. V B and V C are the voltages of B and C with respect to neutral. Now, what is this voltage across this winding? Say this is A phase winding or B phase or C phase? B phase winding. Okay. So, if the B phase winding in the first transformer is V B, okay, it has a voltage V B. What is the voltage in the second transformer which is delta connected? Okay, root 3 V B. And what is this? Root 3 V B. What is this? Root 3. What is V B? V at an angle 0. So, that answers the question, which one is lagging and which one is leading. So, I just took between two terminals B and C. You can take between A and B, C and A also. A and B also gives the same thing. So, so we saw that V B minus V C is root 3 V at an angle 30 means in the delta case it is root 3 V at an angle 0. So, the voltages of the delta winding are lagging the voltages of the Y winding. So, now let us, so shall I go to the other page? Clear? So, if I go back to this circuit, now again I will ask the same question. If gate pulses are given to valve 1 at some instant, gate pulses to valve 1 prime. So, my intention is to operate the two 6 pulse LCCs identically. So, same identical operation is expected from the two 6 pulse LCCs. Okay. So, then at what instant should I give the gate pulse to valve 1 prime with respect to the instant of giving gate pulse to valve 1? Same. See, the voltages which are applied are identical in magnitude. So, the voltages which are applied to the two 6 pulse LCCs are identical in magnitude, but one 3 phase voltage which is supplied, that is coming out from the delta, is actually not identical in phase. It is lagging the voltage which is applied to the first LCC by, that is what we showed just now. The voltages of the delta winding are lagging the voltages of the Y winding by 30 degrees. The same voltages are applied to the two 6 pulse LCCs. Now, I want identical operation of the two 6 pulse LCCs. So, if I give identical operation, that means the gate pulse should be same at the same instant with respect to the respective 0 crossings. So, if I give a gate pulse at some instant to valve 1 in the first LCC, valve 1 prime in the second LCC, the gate pulse should be at an instant which lags or leads, or at the same instant. It should be same. Why it is same? See, there are two 6 pulse LCCs. Okay, I want identical operation, but the voltages that are fed on the AC side are identical in magnitude, but actually different in phase angle. One voltage is lagging the other voltage. So, the gate pulses should also lag by the same amount. So, since the voltages are lagging by 30 degrees, the gate pulses should also lag by 30 degrees. So, what I am trying to say here is gate pulses to the 6 pulse LCC connected to the delta connected winding are delayed by 30 degrees with respect to the instants of, so I would say gate pulses. So, with respect to the instants of gate pulses to the 6 pulse LCC connected to the Y connected winding. Fine. So, now let me give some expressions for these complex currents that I have shown IAH, IBH, ICH. So, if I will just remove this. So, this was just written for the sake of explaining that the gate pulses are delayed by 30 degrees. Yes. So, suppose I take this IAH. So, I said H can take a value of 1 or 5, 7, 11, 13 harmonic component. So, it is either 1 or 6k plus minus 1 for all positive integer values of k. Okay. So, if I take IA1, say IA1. So, I take a special value of H. H can be, say, please recall what is the H value of H. On the AC side, H can be either 1 or 6k plus minus 1. On the DC side, it is 6k. Okay. So, if H is 1, IA1, suppose I say the magnitude is I1 at an angle 0. Okay. If I take IB1, again the B phase current with H equal to 1. Now, what will be the magnitude? Magnitude is same as IA1 and the angle is minus 120 degrees. Suppose I take IC1, the magnitude is again same, the angle is plus 120 degrees. This is as far as the fundamental components are concerned. Now, if I take some harmonic component, okay, say IA5, I use the notation I5, the RMS value of the fifth harmonic current is say I5. Now, what should be the angle? Now, please note, when we talk about taking reference, I can choose independently the reference values for different harmonic components. So, I can again take this as 0. So, if I take B phase IB5, it is having the same magnitude I5. What about the phase angle? 120. How did you get that? Now, so can I say it is minus 120 degree into 5? Yes. Then IC5 is again I5, phase angle 120 degree into 5. So, I take the fundamental angle into 5. Now, I could have simplified this. See, minus 120 into 5 is nothing but 120. Minus 120 into 5 is 120. And plus 120 into 5 is minus 120. I could have simplified this, but I will retain like this. Now, the reason is, what I am trying to convey is, I need not actually write the expressions for this complex current separately for fundamental, separately for fifth harmonic, separately for seventh. I can write a general expression. Suppose I take IAH. See, what I am trying to say is, for H equal to 1, or h equal to 6k plus minus 1, k takes any value. So, for harmonic components as well as the fundamental, we can write a combined expression, I mean which is general for generally applicable for all values of the h, whether it is 1 or 6k plus minus 1. So, what is that? So, can I say that IAH is IH at an angle 0, IBH is IH at an angle minus 120 degree into h. So, it is applicable even for h equal to 1, and ICH is equal to IH at an angle 120 degree into h. Now, these are the currents which are fed to the first 6 pulse LCC. Now, let me take the other currents which are fed to the second 6 pulse LCC. So, they have the notations IAH prime, IBH prime, ICH prime. So, even for these currents, I can write a general expression which is applicable for h equal to 1 as well as 6k plus minus 1. So, what is the magnitude of these currents? It is IH, all have the same magnitude IH. Okay. Now, come to the angle. If I take IAH prime, what is the angle? Minus 30. See, IA1 prime is nothing but I1 at an angle minus 30 degrees. But if you take IA phi prime, it is I phi, what is the angle? Minus 30 into h, so minus 30 into 5. Okay. So, what is the phase angle here? So, I can say this is minus 30 degree h. Okay. What about this? Minus 150 h. See, the idea is very simple. If I take IB1 prime, it is I1 at an angle minus 150. If I take IC1 prime, it is I1 at an angle 90 degrees. So, from that I get IB 5 prime, IB 7 prime, IC 5 prime, IC 7 prime and so on. Okay. So, it is just multiplying that by h. Now, these things are they familiar? How multiplying by h gives phase angle? So, this is ICH prime is having a phase angle 90 degree into h.